Hi everyone, we're going to go through the Leap of Faith handout today. So we have our test person here, Brent, who's going to be jumping, and so we want to track essentially his hips. Imagine we're looking at his belly button here, and so first motion here Brent's going to do, is it going to be up or down, right? Because we're going to be trying to sketch the graph of his vertical position, so the position right along the vertical axis here as time goes on. So we're tracking his belly button. First thing he's going to do is drop down and then jump up, right, and land. So let's take a look at that again. So he's going to drop his hips, jump up, land, and you see that he dips at that landing, right? He dips at that landing. Let's see if we can go through this slow motion. So it dips down, comes up. He's in gravity in the air, slowing down. Now he's going to speed up, and upon landing, he's going to bend his knees and slow down to a stop, then reaccelerate back up, and then slow down to rest. So we're going to have to graph all of that, and I'll revisit this video here in a moment. So we started off at rest. So these graphs that we're going to be looking at, I got to make sure that we're comfortable with the position time graph first. So I'm going to look at some pieces of this, starting with the initial point, and I'm going to be tracking the steepness because the steepness is his speed at that moment. So we start off flat, which is 0. You can see he's going to start to gain downward speed. He's going to stop when his knees are fully bent, right before he's then about to spring up. When he springs up, he's going to start gaining more and more velocity until the point where he is entering the air, at which point he's going to slow down and get less steep, flattening out, gaining downward speed, negative, until he lands back on the ground. And now he's landing, right? So if he's landing, he's going to be slowing down, so eventually stopping, again, when his knees are fully bent down. And then he's going to stand up, so he's going to gain some upward speed as he then stands upright and comes to stop, which is flat. Tracking these red dashes, and in particular their steepness, now as y-axis values, we're going to start with flat, which is a 0 y value. It's negative, and then flat. That's where it is over here. And then if you notice here, it's going to spring up, right, as it gets steeper and steeper and steeper. And then this point up here is that takeoff. No longer getting faster at that point because he's leaving the ground. Okay, and then you see this whole parabola that we have here corresponds to this entire shape in the air here. And that's a special in the air type of motion, which we call free fall. And of course, that's going to be when gravity is acting on him. So you can see the consistent parabola that we have on this middle section while he's in the air that has a concave down is when he is experiencing an acceleration down due to gravity. That slope is going to also be the acceleration of gravity, right? That slope. From there, we are going to be tracking again his steepness. So when he lands, he's going to be flattening out, slowing down. So when he lands, he's going to be slowing down to 0. When this is flat, he's going to then accelerate up a little bit or stopping. If we're tracking the slope of the velocity time graph, that's going to give us these accelerations. So if you notice here, there's a negative slope segment, so negative acceleration. That corresponds to when we had a negative acceleration here. You can see here we have an acceleration due to the concave down. That's this negative acceleration and that negative slope. We then have, piecewise with this, a parabola that is going to be concave up, indicating an acceleration up. Remember, concavity shows the direction of acceleration on a position time graph. That segment corresponds to this linear segment and a positive acceleration due to the slope of that segment, which is the positive constant acceleration here. We already talked about gravity, so that purple highlighted portion is going to be this bottom portion here. And if we follow suit, this concave up portion of the parabola here is going to correspond to that positive acceleration, positive slope portion here. And then we have a little concave down possibly right there, which corresponds to that piece there. So in looking at part B, justify why the initial acceleration downward during takeoff if the takeoff is upward. So why would we have an initial acceleration downward during the takeoff if the takeoff is upward? And that's of course because if we look back at our video here, although he's taking off up, he's going to drop his hips. So if he's starting from rest, his first motion is going to be to speed up down and then immediately start to slow down as he reaches his lowest point and then continue to then speed upward as his takeoff. So there's that initial dip of his bending his knees, lowering his center of mass, and then slowing that downward speed to then spring back up. Compare the takeoff velocity to the velocity with which the student has just before landing. So if we use our graph up here, the takeoff speed here is going to slow down according to gravity to 0 on the way up. And then that same acceleration is going to speed him up on the way back down. So given that the amount of time and distance that he has on his way up is symmetric to the time and distance he has to go back down to the same elevation, the same number value or magnitude with which he leaves the ground on the takeoff up, positive, should be the same number value or magnitude as the negative velocity he has going down upon landing. To answer part D, I'm going to first go over to the video analysis and make sure we're comfortable using that. So if I jump over to video analysis, I have inserted the video, and what we need to do first is figure out which frame we're going to start with, and they actually have this perfectly timed, so we're going to start at frame 1 here. I'm going to go to System to set my scale, and we have the meter stick here that I'm going to line up. So you can see here 563 pixels is 1 meter. That's how we're going to convert then the video to a distance. I'm going to measure from the ground and I'm going to track the side of his hips. So right between his feet, but I'm going to line up the y-axis with his hip. If he was wearing a shirt that was a different color, drastically different color than his pants, I would be easily track where his shirt lines up with his pants. But we're trying to basically track his hips or his center of mass. So I'm going to define this point to be my 0 height. And now we can start to add points. So I'm going to click add. And when I click this, it's going to jump ahead a frame. So I click this and you see there's not much movement there and it made a dot. I'm going to click it again because now I'm seeing them start to lower and I don't like those dots getting in the way of me seeing stuff, so I'm going to turn them off. Many of you went over to here and changed the number of frames it jumps to after you pick a point to 2 or 5. I'm going to keep collecting on 1 frame. And I'm going to go ahead and collect that, not in front of you, so I'm going to pause this and I'll jump right back in. Okay, so now I've actually collected all the points, and I'll show you as I scroll through it that we can see how I tracked all of the points of him in the air. And those are now graphed off to the side. So I'm going to get rid of the video by toggling off the video. And I can see I have these graphs, right? So I don't really care about the left and right axis because we're tracking the vertical motion. So I'm going to turn off the X, and we can obviously look at the Y, or we can look at the Y velocity. So if we take a look at these two, I normally don't like to overlap these two things. So we can take a look at them one by one, depending on what we're trying to look at. Going back to our handout, let's see what it asks for. So we're supposed to determine numerical values for the takeoff speed, the maximum height in the air, which I'm going to measure from his initial takeoff. So like from where his hips are, if he's just standing there, to like the maximum point he has in the air. Since that wasn't really clear, you could just measure from the ground or whatever reference point you have, and that's okay. We're going to measure an experimental value for the gravitational acceleration. I know that's supposed to be 9.8 or 10, but we're going to see what the graph tells us and then compare it. And we're going to get the overall delta t, the time duration that it took him from when he touched the ground upon landing to when he was standing at rest. So let's start with takeoff speed. You can see that highlighted in pink here. So the best thing, since I have both graphs to look at, would be to get velocity, would be to look at the y value where at the moment he's taking off. And we knew that that was going to be that peak value. If I jump over to our graph, then I'm going to look at just the y value up here, and I got 2.87. That's the speed he had at takeoff. The maximum height in the air. So I needed to go over then to my position time graph, ideally, if I have that option. And I'm going to find out where that vertex is at the peak. Found that to be 1.22. And that would be above what I called 0, which would be the ground. I'm going to subtract off his height from the ground to his feet. I'm going to show you on the video here what I mean. So at this value right here, I can see it's 1.22. And when he's just simply standing there, I had that was about 0.48 was his hips. Now, on this, I have 0.56. When I originally did the key, I measured that to be about 0.48. So let's go back to then what I was saying, the difference between this peak value and what we have as his original hip value, I'm going to call how far he jumped in the air. Because I want to know how far was he up in the air from where I started, which was from his hips. So I'm going to track how far his hips moved while in the air. So his hips began to move right around here off the ground, and this was the highest point. So the difference between those 2 points, 1.22 versus what I was tracking as about 0.48, was a difference of 0.74. When you look at that in inches, that corresponds to about 29-inch vertical. So good job, Brent, getting a really high vertical. That's pretty impressive. Moving on, let's look at a gravitational acceleration value from our data. No, it should be 9.8, but if I highlight that portion while he's in the air, I'm going to go to my velocity time graph here because I know slope of that gives me acceleration, and that's going to allow me then to get a negative 11.1 is what I got when I highlighted that section that he was in the air. And I did a curve fit, and you can see here, in this case, I got about 12.1 with the data that I used. So 11.1, 12.1, depending on the video you have, right? So it's a little bit off because it should be 9.8. And the time duration of the landing, all I'm going to do is go highlight the point where he lands to where he's no longer moving. And in that case, I was saying he landed right about here. So I'm going to highlight how long it took from when he began contact with the ground to when he was standing up. And you can see here that the overall range along the x-axis, which is time, is 1.033 seconds. That's what you can see here highlighted in purple. So that's going to be for the front side. Now we have a calculus application follow-up to this. So we're going to say, what if we were to model this as a single function and we were able to do this with a cubic function? So this is a position time function instead of a graph. And so we're going to determine expression for the student's velocity as a function of time by doing a derivative, right? The slope of position time is velocity. So derivatives are slope functions. And we do a power rule here and get velocity as a function of time. To determine the student's takeoff speed, we would, at 0.4 seconds, we could then substitute in 0.4 seconds for t, and that would allow us to calculate the speed at that time, which they're saying in this problem is the takeoff speed. We wanted to calculate the position and time when the student's center of mass was lowest during the takeoff phase. Then this is going to key in on a concept that is going to be seen pretty often in AP Physics, where the lowest point would be where there's a change in direction. And that's a key, right? Because it's the change in direction, you have to be momentarily stopped as you go from a positive velocity to a negative. You have to cross 0. So we know that if we know the velocity is 0, that indicates that we could have a change in direction. So in this problem, we're going to take that original position time function and get the velocity function using a derivative. And we're going to then set that equal to 0, meaning we're going to say v is 0 and solve for the times at which v is 0. And that first time where v is 0 would indicate then the first time that he's changing directions, which would be at that first lowering of the hips and changing direction as he springs up. So the time would be 0.256. Knowing that, I can plug that into my function and solve for the time, the x value at that time. I hope that helps. Let me know if you have any questions.